Hello guys, IBM is here with part 8. I think this is part 8 of magnetic fields and electromagnetic induction. These are past paper questions from 9702, paper 4. Part 8 question, the first question, a metal wheel consists of an axle, 8 spokes and a rim as shown in the figure here. Point X is on the rim at the end of one of the spokes. The rim has a radius of 0.85 meters. The wheel is rotating clockwise. So the wheel is rotating clockwise, that is in this direction here. Okay. With an angular speed of 140 radians per second, there is a uniform magnetic field of flux density 0.18 teslas into the plane. This is into the plane of the page. So we represent into the plane. If you use Fleming's left-hand rule, the first finger points to the page. If the page is on your table, the first finger points to the table. If you hold the page vertically, as you look at my screen, the first finger must be pointing to the page that is away from you, according to Fleming's left-hand rule. State Lenz's law of electromagnetic induction. Of course, we now know that Lenz's law deals with direction. The direction of the induced EMF is such as to produce effects that oppose the change causing it. So direction of induced EMF is such as to produce effects that oppose the change causing it. Of course, we have already stated this, but many times when I write something or when I write a law, it's only because I want to refer to it when solving the question. Show that the time taken for point X to complete one revolution is 45 milliseconds. So time is the period. You know that period is equal to pi over omega, which is going to be 2 pi. Omega is 140. So I'll just press my calculator. 2 pi divided by 40, not 40, is it 140? It is 2 pi divided by 140. So that is 0.449 or 0.0448 seconds. So this is going to be 44.88 seconds. Milliseconds, because I've multiplied by 1,000, which is approximately 45 milliseconds. So that is 45 milliseconds. Calculate the magnetic flux by spoke AX during one revolution. So the time is one revolution. Magnetic flux. We know that flux equals to, now that we are considering one revolution, magnetic flux is equal to B times A. And of course, we know that the area is pi r squared. So the magnetic flux, they gave us the flux density, which is 0.18 teslas. So that is 0.18 teslas. Then the area is going to be pi times the radius. The radius is 0.85. So this is going to be 0.85. So I'll just check my calculator. 0.18. Sorry, this is squared. 0.18 times pi times 0.85 squared. So that is 0.41. 0.41. Because this is magnetic flux, the unit is the Weber. Then the magnitude, determine the magnitude of the EMF induced across spoke X. So of course we know that EMF is equal to the rate of change of magnetic flux. So that is change in magnetic flux divided by T. So the flux here is going to be 0.41. Of course changes from 0 to 0.41. Or I can write more figures here, 0.4086. So 0.4086 divided by the time, which was one complete revolution, which is 45 milliseconds. That is 45 times 10 to the power of minus 3 previously. So this is going to be 0.4086 divided by 45 exponent minus 3. So that is 9.08 volts or 9.1. Use Lenz's law to explain whether the potential is higher at end A or end X of the spoke. So the reason as to why I stated Lenz's law here. Remember, the direction of the induced EMF is such as to produce effects that oppose the change causing it. So according to Lenz's law, the force must oppose the clockwise rotation. Because the rotation is clockwise, the force must oppose the clockwise rotation. That's why the thumb is pointing in the opposite direction to the rotation. According to Lenz's law, the force must be in a direction which opposes the clockwise rotation. Therefore, the thumb of Fleming's left-hand rule must be in the opposite direction to rotation. And with the first finger pointing onto the page and the thumb pointing in that direction, you notice that the second finger points towards the right-hand side. So using Fleming's left-hand rule with the first finger pointing into the plane of the page or into the paper, and the thumb pointing upwards, that is in the opposite direction to rotation, then the second finger, which shows current, is going to point to the right, as I've illustrated here. It's very clever, although abstract, to think of the section AX. We can think about the section AX as a battery. So the section AX is going to act as if it is a battery. Let's say this is AX. And the second finger is showing that the current is moving from A to X. The current is moving from A to X in that direction. So it's very clever, though abstract, to think of section AX as a source of EMF, just like the cell. So if current through the battery is moving from A to X, then this side is going to be positive, this side is going to be negative. Just like when you look at a cell, we know that if we have a cell, current originates, we saw that current is from positive to the negative terminal like this. So that means through the battery, current goes in that direction there. So if current through the bicycle spoke flows from A to X, then it means X is positive and A is going to be negative. So in fact, positive charges are going to be pushed outwards by the magnetic force, as shown here. They're always going to be pushed towards X, making X to be positive. Okay, therefore, to answer this question, we shall simply say that by Lenz's law, the force on the spoke must be anticlockwise or counterclockwise. So the force must be anti-clockwise or counterclockwise. And applying Fleming's left-hand rule, I think Fleming's is a single M. Applying Fleming's left-hand rule, the induced current is from A to X. So X is at the higher potential. Now do not think about this as if it is an electric field, because we know that an electric field, the charge carriers, which are the electrons, move from lower potential to high potential. Because this is a section of a conductor which is moving in a magnetic field, it behaves as if it is now a source of EMF. And if we think about it as a source of EMF, just like a cell, if current is leaving A to X, then this section here is like a cell where we know that current from the cell leaves from the positive to the negative if you connect it across an external component or across something else in a circuit. Therefore, the end towards which the end towards or the end towards which the positive charge carriers are swept is going to become more positive, or the positive ions are going to be pushed towards or outwards towards point X, making X positive and making A negative. Just like for a cell, if current through the cell flows from the negative terminal to the positive terminal, then we notice that the end where the current flows to is actually going to be where the current starts from to go to the external circuit. So this side being positive, the other side being negative. So X is going to be at higher potential as compared to A. A long straight wire carries a current into the page. So this is into the page. We use a cross as shown here. On the figure, draw 4 field lines to represent the magnetic field around the wire due to the current in it. So we have already demonstrated this using the right hand grip rule or the corkscrew rule. Imagine gripping a conductor in your right hand with the thumb pointing towards the direction of the current. So your thumb will point toward into the page while gripping a pen in your hand, and the magnetic field due to a current carrying wire are concentric circles whose separation increases as you move away from the wire, to show that the field becomes weaker as you move away from the wire. So you should draw very beautiful concentric circles. I always encourage my students to use a compass to draw very beautiful concentric circles, and we say the direction of the magnetic field is going to be clockwise as predicted by the right hand grip rule. Gripping a conductor in your right hand, the fingers fold in that direction. Okay, two identical wires X and Y are placed parallel to each other. They are parallel to each other. The wires both carry current into the page. So the current is flowing in the same direction. Of course, by simple logic, when current flows in the same direction, the force is attractive. Explain why the two wires exert a magnetic force on each wire. So if wire X and Y are close to each other, it means each wire is sitting in the magnetic field of the other. Therefore, because there's a current in the wire, and yet each wire is sitting in the magnetic field of the other, and yet the magnetic field is perpendicular to the direction of the current, by Fleming's left-hand rule, there will be a force. There will be a force on the wire whose direction is predicted by Fleming's left-hand rule. Therefore, To explain why the two wires exert a magnetic force, we shall say that the current so again my pen has stopped. So the current in each wire creates a magnetic field around the wire. So the current in each wire creates a magnetic field around the wire. So each wire sits in the magnetic field of or in the magnetic field created by the other wire. Each wire sits in the magnetic field created by the other wire. So the current, of course, the current in one wire is going to be perpendicular to the magnetic field. Imagine the current is into the page, but the magnetic field lines are concentric circles in the horizontal plane. So that means the magnetic field is actually perpendicular to the current. So the current is the current in one wire is perpendicular to the magnetic field due to the other wire. Due to the other wire. So each wire experiences a magnetic force according to Fleming's left hand rule. So according to Fleming's left hand rule, each wire experiences a magnetic force. On figure 7.2, draw an arrow to show the direction of the magnetic force exerted on wire X. Label your arrow F. Okay, so I'm going to just use the Fleming's left hand rule, which I indicated here. Think of a single magnetic field line around wire Y, which extends and passes through the position of wire X, as shown by this. I'll just draw one concentric circle around wire Y, which goes through wire X. According to the right-hand grip rule, the direction of this is in that direction there. The direction of the magnetic field is in that direction there. And at the position of wire X, the magnetic field is vertically upwards. So B is going to be vertically upwards. So if B is vertically upwards, yet the current is into the page, so first finger of current is into the page, second finger of field is vertically upwards. If the paper is on your table, then you notice that the thumb points to the right hand side. Therefore, the arrow we are looking for here, of course, this is just to show you, you do this using a pencil. So the arrow we are looking for here is going to be in that direction here. So this is the direction of the force. If I rub all these other arrows, the current in X is double the current in Y. So we are doubling the current in X. State how the magnetic force exerted on Y compares with the magnetic force exerted on wire X. So even though the current is double, we know that the force, by Newton's third law, the forces are equal in magnitude but are in opposite directions. So by Newton's third law, the forces are equal in magnitude but are in opposite directions. So the forces are equal in magnitude but they're in opposite directions. Or you could say the force between the wires depends on the product of the wires, and therefore the product of the wire is the same for each wire. I mean the product of the current in the wire is the same for both wires, therefore the force is going to be the same. So by Newton's third law, the forces are equal in magnitude but are in opposite directions. Okay. The direction of the current in both wires is now reversed. So both directions are reversed. State with the reason the effect of this change on the direction of the force on the wire. Of course, there is no effect here because if the current was in both directions downwards, the force is always attractive. If current is changed to be in that direction again, the force is still going to be attractive. So there is no change. No change in direction, no change in direction of the force. Because when the direction of the current changes, both magnetic fields also change or reverse immediately. So no change in direction of force since both the current in X and the field due to Y have reversed at the same time. So if we reverse the direction in both wires is reversed, it also means that the magnetic field due to the current in Y is going to reverse. So in that case, if you draw the concentric circle, now the magnetic field will reverse and to be pointing in this direction here. At this point, it will be vertically downwards. But of course, remember the current here will be out of the page. So first finger downwards, and then the second finger out of the page. Still, the thumb will point to the the right hand side. So that means there will be no effect. There will be no effect because the current in X and the magnetic field will both reverse direction. What have I done? Okay. A particle of charge positive q, and mass m is traveling in a vacuum with the speed v. The particle enters at right angles. At right angle, a uniform magnetic field of flux density B as shown below. So the particle enters at 90 degrees to a uniform magnetic field. State the direction of the magnetic field. The particle leaves the magnetic field or the field after following a semicircular path of diameter d. So of course, since this path is towards the right, it means the force at entering in the magnetic field is going to be towards the center of the circular path. So the particle is positive by Fleming's left-hand rule. The second finger, which represents the direction of current, points in the same direction as the positive particle. So the second finger must point in the direction in which the particle is entering the magnetic field. The thumb points in the direction of the force, which is towards the center of the circular path. So when you try to use your left hand, as shown in this diagram here, with the first thumb pointing towards the right, first finger pointing upwards, you notice that the first finger will be pointing towards you, the second finger pointing in the direction of the current. Place your left hand on the table if the paper is on the table, and you'll notice that actually the first finger points towards you. So that means if then you think about the paper as being vertical or holding it vertically, that means the thumb is going to still point to the right hand side, holding the paper vertically on the table, with the thumb pointing to the right hand side and the first finger pointing upwards, that is vertically upwards in the same direction as the positive charged particle. So you'll notice that actually the field is going to be out of the page. So this is going to be out of the plane of the page. Out of the plane of the page. Explain why the speed of the particle is not affected by the magnetic field. Of course, the magnetic force is always constant and is always perpendicular to the direction of the velocity or the direction of the speed. So the magnetic force does not change the speed, it just changes the direction. Therefore, it just provides the centripetal force or the centripetal acceleration. So we shall say the force on the particle is always perpendicular to the velocity or direction of travel. The force on the particle is always perpendicular to the velocity stroke direction of travel. So there is no work done because if the force is perpendicular, it does not change the speed, it just changes direction, so there is no work done. So there is no work done. There's no work done by the force on the particle since acceleration is always perpendicular. Is always perpendicular to the velocity. So the magnetic force on the particle is always perpendicular to the velocity or direction. That means therefore the acceleration is always going to be perpendicular to the velocity, and if the acceleration is perpendicular to the velocity, then the force cannot do any work. It simply just keeps changing the direction. So the particle, the speed of the particle is not always going to be affected. Show that the diameter d of the semicircular path is given by that expression. So like I said, the magnetic force provides centripetal acceleration or centripetal force. Therefore, we shall say magnetic force is BQV, centripetal force is mv squared over r, and we know that the radius equals 2, since they gave us the diameter here as d, so the radius is going to be diameter divided by 2. So we shall say that BQ equals mv, where there is r, I'll put d over 2. So this means that d over 2 BQ is going to be equal to mv, and we try to make the subject, so d is going to be twice mv divided by b times q as required. Use the expression in B Roman 2 to show that the time tf spent in the field by the particle is independent of its speed. You and me know that the time is equal to distance divided by the speed. And of course, the distance covered is actually the circumference of this path, which is half of a circle, or it is a semicircle. So the distance is going to be the circumference. So the circumference of that is pi d divided by 2. Because the circumference of a full circle is pi d, so half a circle is pi d over 2. So that means the time, which is tf, is going to be the distance, which is pi d divided by 2, then divide by the speed. So I will divide this by v. Divide this by v, and this is going to be equal to pi d over twice v. But then d is 2mv over bq. So tf is going to be pi into 2mv divided by bq, then divide this by 2v. So 2 cancels, v cancels. So this is going to be equal to pi m divided by b times q as tf. So hence, we don't see, they said to show that tf is independent of v. So we notice that hence tf is independent of v. So the time is independent of v as required. I think part 8 should stop there. See you in part 9.